Hi everyone, I'm Chen Zixia from CSBL. Today my presentation title for the journal club is Therapeutic Manipulation of Gut Microbiota by Polysaccharides of Wolfiporia cocos reviews the contribution of the gut fungi-induced PGE2 to alcoholic hepatic steatosis, which published on Gut Microbes on 2020. The gut-intestinal barrier is directly impacted by alcohol intake, both acute binge drinking and chronic alcohol use. This is due to the effect on tight junction between gut epithelial cells, mucin formation, and the recruitment and activation of inflammatory cells to the intestinal wall. Additionally, drinking alcohol alters the composition of gut microbiota. As a result, there is a greater transfer of microbial product via the portal circulation from the gut to the liver. Other microbial components may also enter the liver in addition to elevated LPS levels. Once inside the liver's sinusoid, Kupffer cells and other recruited immune cells become activated and generate significant amount of pro-inflammatory cytokines such as TNF-alpha, IL-1 beta, and IL-6. The majority of these cytokines exacerbate intestinal permeability, which feeds the inflammatory vicious circle associated with alcoholic hepatitis. The experimental design is illustrated in Figure A. Compared to the alcohol group, oral administration of WIP reduced the level of ALT, ALP, and LDH in the plasma, indicating a significant alleviation of liver injury with WIP treatment. Additionally, after WIP supplementation, the levels of TG and TC in the liver decreased, suggesting a significant reduction in alcoholic hepatic steatosis. Red oil staining revealed that WIP could reduce hepatic fat accumulation. Previous studies have indicated that MCP1 can promote macrophage activation, pro-inflammatory responses, and hepatic steatosis. In this study, immunohistochemical analysis found that WIP treatment effectively reduced the expression of MCP1 in the livers of chronically ethanol-treated mice. Subsequently, the composition and abundance of the gut microbiota were analyzed to investigate the impact of WIP on the gut microbiota of mice with ethanol-induced liver injury and steatosis. The study found that long-term ethanol consumption significantly reduced the alpha diversity of the gut microbiota, decreasing the abundance of firmicutes and increasing the abundance of proteobacteria. Oral administration of WIP prevented the ethanol-induced reduction in firmicutes, specifically inhibiting the decrease in firmicutes at the genus level, such as Blotia, Rumini Clostridium, and unidentified Clostridians. The study suggests that changes in the gut microbiota of ethanol-fed mice are associated with alteration in intestinal barrier permeability and metabolic endotoxemia. Therefore, the expression of tight junction proteins was assessed using RT-qPCR. It was found that WIP treatment significantly counteracted the alcohol-induced decrease in mRNA expression of ileum tight junction proteins, ZL-1 and aclondin, as well as the reduction in plasma lipopolysaccharides. By a quantitatively PCR measurement shows a significantly increase in fungal populations in feces of ethanol-treated mice. WIP treatment effectively inhibited ethanol-induced fungal overgrowth. The obligate anaerobic bacteria plays a dominant role in maintaining the hypoxic microenvironment by activating PPAR gamma signaling pathway via intestinal butyrate and inhibiting colonic inflammation. In summary, the reduction of firmicutes and bacteroidetes induced by alcohol may lead to the inactivation of intestinal PPAR gamma signaling, which could be one of the mechanisms for fungal expansion in the gut of animals or patients with alcoholic liver disease. In the present study, PPAR gamma signaling was found to be downregulated. PPAR gamma expression was reduced, and NOS2 expression was increased in ethanol-induced mice. In addition, elevated levels of chronic TNF-alpha and IL-1 beta indicated that chronic ethanol consumption led to the development of a pro-inflammatory response in colonic tissues. WIP treatment activates the PPAR gamma signaling and reduced inflammation in colonic epithelial cells, which prevented overgrowth of intestinal fungi and proteobacteria. Fungal strains were cultivated using Dixon agar, the best medium reported in the cultural mix method, which led to the identification of intestinal fungi directly associated with AHS. Cultivation data further confirmed the amplification of gut commensal fungi in mice receiving ethanol, especially in the overgrowth of Myrozyma gillemontii, and ITS sequencing also showed that Myrozyma gillemontii fungi were enriched in the gut of ethanol-induced mice. To test whether the overgrowth of Myrozyma gillemontii was associated with the development of AHS, antifungal treatment with amphotericin B was administered for 6 weeks, thereby protecting the mice from the ethanol-induced liver injury for the next 6 weeks. However, fat accumulation and inflammatory damage were exacerbated when ethanol-free mice without the fungus were subsequently given Myrozyma gillemontii. Also, the addition of Myrozyma gillemontii increased the plasma beta-glucan levels. The above evidence confirmed that the Myrozyma gillemontii in the intestinal tract of mice contributes to AHS development. The study suggests that endotoxin stimulated production of PGE2 in the liver, dependent on hepatocyte PGE2 receptors EP2 and EP4, promotes the accumulation of triglycerides. The expression of ELR-positive CXC chemokine CXCL1 is also correlated with neutrophil infiltration in patients with alcoholic hepatitis. Chronic ethanol consumption significantly elevated the hepatic levels of PGE2, along with increased expression of EP2, EP4, and CXCL1. In WIP-treated AHS mice, hepatic levels of the PGE2 as well as the expression of EP2, EP4, and CXCL1 are markedly reduced compared to the alcohol group. It has been reported that gut fungi-induced PGE2 production is attributed to allergic airway inflammation associated with gut fungal overgrowth. To see whether the increase in PGE2 in the liver of chronic AHS mice were associated with the expansion of gut fungi. Ethanol-treated mice were given an oral ethanol diet with amphotericin B or caspofungin for 5 weeks. It was shown that antifungal treatment significantly reduced the hepatic PGE2 levels and expression the EP2, EP4, and CXCL1. In contrast, inoculation of mice with Merozyma guillemondiae increased the hepatic PGE2 levels and the expression of EP2, EP4, and CXCL1. Moreover, mice receiving oral PGE2 also exhibited features of the alcoholic hepatic steatosis and increased expression of EP2 and CXCL1. To further demonstrate the relationship between gut fungi-induced PGE2 and AHS, ethanol-fed mice pre-treated with amphotericin B were injected with Merozyma guillemondiae, along with the PGE2 synthase inhibitor indomethacin. The study found that indomethacin treatment significantly inhibited the impact of Merozyma guillemondiae on hepatic PGE2, EP2, EP4, and CXCL1, confirming that the gut fungi-induced PGE2 production promotes the occurrence of AHS in mice. In the alcoholic hepatic steatosis mice model, oral administration of Wolfiporia cocos polysaccharide can alleviate liver inflammation damage and fat accumulation. Furthermore, WIP reduces gut dysbiosis and fungal overgrowth in AHS mice, significantly increasing the ratio of firmicutes to proteobacteria, suppressing ethanol-induced fungal overgrowth. WIP activates the PPAR gamma signaling pathway in intestinal epithelial cells, alleviating inflammation, promoting a hypoxic state, and thereby inhibiting the overgrowth of fungi and proteobacteria induced by alcohol. In AHS mice, the fungus Merozyma guillemondiae proliferate excessively, contributing to increased level of PGE2 in the liver, thereby exacerbating AHS. That's all. Thanks for your listening.